The basic concept of subsonic airflow and the resulting pressure differentials was discovered by Daniel Bernoulli, a Swiss physicist. Bernoulli's principle, as we refer to it today, states that, as the velocity of a fluid increases, the static pressure of that fluid will decrease, provided there is no energy added or energy taken away. A direct application of Bernoulli's principle is the study of air as it flows through either a converging or a diverging passage, and to relate the findings to some aviation concepts. Bernoulli's principle was originally stated to explain the action of a liquid flowing through the varying cross-sectional areas of tubes. A tube is shown in which the cross-sectional area gradually decreases to a minimum diameter in its center section. A tube constructed in this manner is called a Venturi or Venturi tube. Where the cross-sectional area is decreasing, the passageway is referred to as a converging duct. As the passageway starts to spread out, it is referred to as a diverging duct. A good application for the use of the Venturi principle is in a float-type carburetor. As the air flows through the carburetor on its way to the engine, it goes through a Venturi, where the static pressure is reduced. The fuel in the carburetor, which is under a higher pressure, flows into the lower pressure Venturi area and mixes with the air. A converging shape is one whose cross-sectional area gets progressively smaller from entry to exit. You can see a converging shaped duct, with the air entering on the left at subsonic velocity and exiting on the right. Notice that the air exits at an increased velocity and a decreased static pressure when looking at the pressure and velocity gauges, and the indicated velocity and pressure. The unit leaving must increase its velocity as it flows into a smaller space, because a unit of air must exit the duct when another unit enters. In a diverging duct, just the opposite would happen. From the entry point to the exit point, the duct is spreading out and the area is getting larger. With the increase in cross-sectional area, the velocity of the air decreases and the static pressure increases. The total energy in the air has not changed. What has been lost in velocity, which is kinetic energy, is gained in static pressure, which is potential energy. As discussed in Bernoulli's principle earlier, a Venturi is shown again, only this time a wing is shown tucked up into the recess where the Venturi's converging shape is. There are two arrows showing airflow. The green arrow shows airflow within the Venturi, and the red arrow shows airflow on the outside heading toward the leading edge of the wing. In the converging part of the Venturi, velocity would increase and static pressure would decrease. The same thing would happen to the air flowing around the wing, with the velocity over the top increasing and static pressure decreasing. The air reaching the leading edge of the wing separates into two separate flows. Some of the air goes over the top of the wing and some travels along the bottom. The air is flowing past a cambered surface, such as an airfoil, and the effect is similar to that of air passing through a restriction. As the air flows over the upper surface of an airfoil, its velocity increases and its pressure decreases, an area of low pressure is formed. There is an area of greater pressure on the lower surface of the airfoil, and this greater pressure tends to move the wing upward. The difference in pressure between the upper and lower surfaces of the wing is called lift. 3/4 of the total lift of an airfoil is the result of the decrease in pressure over the upper surface. The impact of air on the undersurface of an airfoil produces the other 1/4 of the total lift. For the wing shown, imagine it is 5 feet wide and 15 feet long, for a surface area of 75 square feet. If the difference in static pressure between the top and bottom is 0.1 psi, there will be 1/10 pounds of lift for each square inch of surface area. Since there are 10,800 square inch of surface area, there would be 1,080 pounds of lift. Thanks for watching.